In this video, I will analyze the high-resolution infrared spectrum of HCl molecules. A HCl molecule may absorb an infrared photon and undergo the vibrational excitation and rotational transition. The rotational transition can be excitation or de-excitation. When the rotational excitation occurs, its rotational quantum number J must increase by 1. When de-excitation occurs, J must decrease by 1. And therefore, we see the P branch on the right-hand side of the spectrum with lower wave numbers because they correspond to the rotational de-excitation. On the left-hand side, we see the R branch data with higher wave numbers. Again, in the R branch, J must increase by 1. So the first doublet corresponds to the 0 to 1 rotational excitation. But why is this a doublet? With two slightly different wave numbers and quite different absorbance. This is because in nature we have two different chlorine isotopes, chlorine-35 and chlorine-37. There is 75% of chlorine-35 and 25% of heavier chlorine-37. Hydrogen chlorine-37 has a slightly greater reduced mass and therefore slightly smaller wave number. So again, these two differ by only 2 inverse centimeters. And now let's pay attention to this unit. This means 1 wave per centimeter. It's equal to 100 waves per meter. So when we convert this number to the SI unit, it's going to be 290,590 waves per meter. So what I will do is I will simply use the first 2 data points in the R branch and the first 2 data points in the P branch to show you how to do the calculations. For your own calculation, you need to include 1, 2, 3, 4, 5, 6 R branch data and also 6 P branch data for the hydrogen chlorine-35 molecules. You may ignore those lower peaks in the doublets. They are hydrogen chlorine-37. Now let's look at the Excel spreadsheet. Again, what I will do is I will enter the rotational quantum numbers and the corresponding wave numbers. Over here, this is the rotational quantum number, this is the wave number. But you may ask why it's M here. This is because to pull R branch and P branch data in the same Excel graph, we need to do some mathematical transformation. This M equals the initial J value plus 1 for the R branch data. Again, if you look at this spectrum, this wave number is 0 to 1 rotational excitation. The initial J value is 0. So M equals 0 plus 1. Over here, this is 1 to 2 rotational excitation. The initial J value is 1. Therefore, M equals 2. That's why in the first 2 rows here, we have M equals 1, M equals 2. This first one, wave number 2905.9, the second wave number 2925.6. They are 2905.9 and 2925.6. Similarly, we need to do some transformation. Over here, M equals negative J. So for this wave number, it's 1 to 0 de-excitation. The initial J value is 1. Therefore, M equals negative J, M is negative 1. Similarly, M is negative 2 here. and I entered these two wave numbers also in the same Excel spreadsheet, these two wave numbers. And again, m equals negative j, therefore m is negative 1 and negative 2. For convenience, let's convert this for wave numbers to the SI units. Again, meter is the SI unit of length. 1 inverse centimeter is equal to 100 inverse meter. Therefore, I have this number equals the value in the B2 cell times 100. And then we select this data points and click Insert, and then look at the chart, and we get scattered data. 1, 2, 3, 4 data points. All right, and then of course you need to label the horizontal axis, the vertical axis. The vertical axis is the infrared wave number of the photons. The unit is inverse meter. The horizontal axis is the value of m. Again, m is defined to be negative j for the p branch. M is j plus 1 for the r branch. We do this to pull the p branch data and r branch data in the same Excel graph with the same equation. So now we have 4 data points here. We do a second order polynomial equation fitting. So format trend line over here. What you need to do is you need to display the equation, display the r squared value, and also make sure you choose polynomial instead of linear. The order is 2, so it's going to be a quadratic equation. All right, once you do that, you will display this quadratic equation, second order, and r squared is just 1. Again, this video is to show you how to do the calculation, but not to get the exact results. Therefore, I will not pay attention to those sig figures. For your own calculation, be sure to include at least 5 or even 6 sig figures and follow the rules of significant figures. So right now I'm using this second order equation to fit the data points. If you have included 12 data points, again you will get a similar quadratic equation with a very good r squared value. If your r squared value is much different from 1, usually that's because you entered wrong wave numbers. And also pay attention here, this is 0 here. This corresponds to pure vibrational transition. There's no rotational excitation or de-excitation, therefore this is forbidden. We cannot observe this wave number. The selection rule for the vibrational transition is n equals plus minus 1. It must change by 1. The selection rule for the rotational transition is also j equals plus minus 1. It's going to be rotational excitation or de-excitation. Again, higher wave numbers, we're talking about rotational excitation. Lower wave numbers, lower energy, that's rotational de-excitation. Over here, again, this is just the pure vibrational transition. Well, what's this number? Actually, it's just 288565 when x equals 0. All right. So now we get 3 coefficients in front of x squared, x, and x to the power of 0. Remember, this x is actually m. And then in the line menu, we have nice quadratic equation. This wave number of the infrared photon is equal to a quadratic function of m. Therefore, this equation corresponds to this equation. This coefficient, negative alpha e, is negative 30. This 2 times b minus alpha e is 2057. This omega 0 to 1 pure vibrational transition wave number is simply this 288,565. So what we do is we tabulate the value of alpha e here. It's 30 inverse meter. 2 times b sub e minus alpha e over here is 2057 over here. What about the last one? This omega from 0 to 1, this is the vibrational transition wave number. Over here, omega from 0 to 1, the number is 288,567. I'm sorry, 565, coming from this quadratic equation here, this coefficient. Now, since we know the value of alpha E and also 2 times BE minus alpha E, we can compute BE. First, this number divided by 2 will give you BE minus alpha E. And also, BE equals this number plus alpha E. Therefore, this is the calculation. 1028.5 is BE minus alpha E. This 30 is alpha E. We sum it up, we get BE. Alright, so this is my BE, the rotational constant. There's an equation for the rotational constant. H bar squared over 2I equals HCBE. This is by definition. This is by the definition of B sub E, so there's no reason for this. And by using this equation, we can compute the moment of inertia given B sub E. It's very simple. H bar squared over 2HCBE is the moment of inertia. So let's look at this equation. H bar squared. Again, I'm not worrying about the accuracy. I'm going to say H bar is just 1 times 10 to the power of negative 34 joule second. So this is H bar squared, this part. Divided by 2. Divided by H, the Planck constant. Divided by the speed of light, c. And then divided by B sub E. All numbers are in the SI unit. Therefore, the final unit should be the SI unit. The moment of inertia is the reduced mass times the radius squared. Therefore, the unit must be kilogram times meter squared. The value is this. Why do we need this number? If we also know the reduced mass of this HCl-35 molecule, we will be able to compute the bond distance. That's very important. So what's the reduced mass of HCl? Simple. It's 1 times 35 divided by 1 plus 35 atomic mass unit. Again, I am not worrying about the accuracy. What you need to do is you need to replace this 1 with 1.008 atomic mass unit, and also 35 with a more precise number for the mass of chlorine 35. Alright, so again, mu is M1 times M2 over M1 plus M2. The unit is AMU, atomic mass unit. However, this atomic mass unit is not the SI unit. The SI unit is kilogram. So what I will do is I will convert it to kilogram. It's very simple. It's just this number divided by weight times 0.001. Okay, this is to convert gram to kilogram, and divided by Avogadro constant. So again, I'm not worrying about the accuracy here. The Avogadro constant is 6.02214,076 times 10 to the power of 23 exactly, by definition. So again, this is the reduced mass of this HCl-35 molecule in kilogram. Now we have the reduced mass, we can get the bond distance. The bond distance is also called internuclear distance because the bond distance is the distance between the hydrogen nucleus and the chlorine nucleus. Alright, so we know the equation for the moment of inertia. It's mu times r squared. Therefore, this bond distance is simply the square root of I, the moment of inertia, divided by the reduced mass. What's the unit? The unit is meter. So I'm going to put meter here. And the more commonly used unit for the bond distance is angstrom. Or A with a small knot on top. 1 meter is 10 to the power of 10 angstroms. So this is what we have. It's about 1.2 angstroms. What I will do is I will change the number of sig figures. The reason is I don't want you to be misled about the precision or accuracy of my calculations. The actual number, I think, is going to be between 1.2 and 1.3 angstroms. But again, you need to keep 5 sig figures or even 6 in the calculations. Okay, this is a very important achievement. This is how experimentally scientists determine the bond distance for a diatomic molecule. All right, so we have this omega from 0 to 1. That's 288,565 inverse meter. If we also have the pure vibrational transition from 0 to 2, we will be able to compute omega E and omega chi. What's the physical meaning of omega E? This is the vibrational frequency for a harmonic oscillator. Omega E chi is the correction for the enharmonic factor. So this chi is the nth harmonic factor. Alright, so this omega 02 is provided to you in the lab manual. So over here, we got the lab manual here. There's a page of physical constants. Right over here. Again, this is HCl-35. Later, you will work on this DCl-35. So let me just copy this number first. Again, the unit is inverse centimeter. I'm going to convert it to inverse meter. So it's omega 0 to 2. So these two are the vibrational transitions from 0 to 1 and from 0 to 2. Right, so now we can use these two numbers to compute omega E and omega E chi. So first, omega E. How do we do this? If you look at this omega E chi as a whole, just treat this as a variable and then multiply the first equation by 3. And then you will have 3 times omega 0 to 1 equals 3 omega E minus 6 omega E chi. And then this minus 6 and this minus 6 can cancel. Therefore, omega E is simply 3 times omega 0 to 1 minus omega 0 to 2. So this is what I'm going to do here. 3 times this guy minus this guy. All right, and what's the unit? The unit is 1 over meter. Now, omega E chi. The product of this two is equal to, very simple. This time, what we're going to do is we're going to use omega E minus this omega from 0 to 1 and then divide it by 2. All right, so this is the harmonic frequency or harmonic wave number minus this real vibrational wave number divided by 2. What's the unit? It's going to be 1 over meter. So this is the product of omega E and chi E. So I'm going to compute chi E here. Chi is a Greek letter. What's the unit of chi-e? There's no unit. Why do we need chi-e? Now, this time, we will be able to compute the depth of the potential energy well of HCl. So this d sub e times h, the Planck constant, times c, the speed of light, will give us the depth of the potential energy well. But let's do this dE first. dE equals omega e over 4 chi-e. So we have omega e equals omega e divided by 4 divided by chi-e. What's the unit? The unit is 1 over m. And then the depth of the potential energy well of HCl is just Hc times d sub e. Again, I'm not worrying about the accuracy, but you should. There's a problem here. The unit is joule. This is the potential energy depth of HCl. And we can convert this number to kilojoule per mole by multiplying this number with the Avogadro constant. I forgot one thing. This is going to be joule per mole, so now it's kilojoule per mole. Now we have the bond, the depth. Again, this is the depth of the potential energy well of HCl, but it's not the bond energy. To get the bond energy, we need the 0-point vibration energy. How do we get this? Well, we're going to use this equation. We learned that for a harmonic oscillator, the vibration energy is just h nu, h times the frequency, or hc omega, the Planck constant times the speed of light times the wave number divided by 2. And then if it's a enharmonic oscillator, we need to take this enharmonic correction into account. So what I will do is I will just type h, Planck constant, and types the speed of light. And then what we're going to do is we're going to do omega e. Again, this is SI unit, so this is really nice. Divided by 2. And minus omega e chi-e. So over here, divided by 4. Alright, this is also in joule. And I will convert this vibrational 0-point vibration energy to kilojoule per mole as well. So again, it's this number times Avogadro constant divided by 1000. Right, that's roughly 17 kilojoule per mole. So the bond energy equals the depth of the potential energy well minus the 0-point vibration energy. The unit is kilojoule per mole. Now we have the bond energy of this HCl-35 molecule. You will see if you have HCl-37, DCl-35, DCl-37, you will get very similar bond energy. I'll let you think about the reason. Okay, we're not done yet. This is just the bond energy. I'm going to highlight this because it's important. All right, and again, these two numbers are not very accurate. I don't want to mislead you, so I'm going to just use 0 decimal place here. You need to be able to get more accurate result than this. Now the force constant. What we need to do is we need to use this equation. For a harmonic oscillator, the frequency is equal to 1 over 2 pi times the square root of k over mu. And since we have the harmonic frequency and we have this mu, it's very easy to get this k. So how do we do that? Very simple. We're going to have this 2 pi times this omega E times C, and then we square it, and then times mu. So force constant is equal to, again, it's going to be mu, so we'll have to find the mu here in the SI unit. So mu times something squared. What's squared? 2 pi times omega E times C squared. So 2 times pi, I think pi, I'm going to just use 3.14. That's my pi. But you can use 3.1415926, etc. as your pi. And times omega E. I got my omega E here. And the speed of light is right here. Right, we got force constant. What's the SI unit of force constant? It's Newton per meter. And I'm going to highlight this because it's important too. By the way, what is Newton? Newton is force, right? Okay, so when we're talking about force, the unit of force is simply the unit of mass times the unit of acceleration. So Newton is just kilogram times the unit of acceleration, second to the power of negative 2. All right, so if you look at this, meter and meter cancel. So kilogram divided by second squared is also the SI unit of the force constant. It looks weird, but these two units are exactly the same. So now we have the force constant. What else? I'm going to highlight Chi. That's one of the lab goals. And I think I'm going to highlight the bond distance in meters. That's one of the lab goals. And I'm going to highlight those equations we use. Okay, it's difficult to highlight those. Those are actually images of the equations. So I'm going to just ask you to look at these equations again before I end this video.